We've been talking about covalent compounds, what feels like forever. We've been drawing their dot structures and looking at the polarity of the bonds and the shape of the molecule, the polarity of the molecule, and now we've been looking at these intermolecular attractions that are between the molecules. And sometimes you say, why do I care? Well, we care because it affects the properties of the substance, and that's what we can really study in the lab. And if I'm doing a particular reaction, I might need a substance that has certain properties. I'm designing a certain material and I want it to have a high melting point, or I want it to be really durable. Well, then we have to think about the properties of the substance, and often it's a function of their intermolecular forces or interparticle forces. And so some of these properties that are dependent on the strength of intermolecular forces are things like melting point, boiling point, like just phase in general. Volatility. Volatility looks at the ability of something to evaporate. So liquids can evaporate, going from the liquid phase to the gas phase. But how easy does that happen? Well, it depends on how strongly the particles are attracted to each other. So if we have something like bromine, liquid bromine. Ooh, that's not going to work. Liquid bromine. Here we go. Is a diatomic molecule. It's just Br2. But if I draw its structure, because I feel like I'm getting really good at this, it's pretty simple. Just a bromine and another bromine. They both have their 7 valence electrons. There they go. Link them up, single bond. And now I can look at the structure and say, oh, that's totally nonpolar. Obviously, it's the same atom bonded to himself. And so if it's nonpolar and the electronegativities of the atoms are exactly the same, then for the most part, they're sharing the electrons the same. And the only chance I have of getting any kind of a charge out of that thing is just from the temporary unequal distribution of electrons. Because the electrons in that bond are always moving, just by chance their movement might put them so that for a moment in time they're not right in between the two bromine, and then I would get that temporary charge. Well, eventually if that happens to a couple molecules and the opposite charge is aligned, we can create those weak dispersion forces in between the molecules. But because those dispersion forces are weak, it doesn't take much energy to separate the molecules. It's like the molecular glue between the molecules is really weak. So it's easy to break them apart. We would say that it's a volatile liquid then. And in fact, it is kind of like a dark reddish brown liquid. And it vaporizes really quickly. And you see kind of this orangey brown gas on top of the liquid. Now, unfortunately, it's toxic. So you got to be really careful when you use liquid bromine because it does evaporate really quick. Now that might be in comparison to something like ethanol, where ethanol is a little bit different molecule. It's got 2 carbons. They end up being single bonded. Then you got some hydrogen. That's kind of a funky looking hydrogen. Hydrogen surrounding the carbon, because carbon needs an octet, so he needs 4 bonds. But then on one end, you have kind of a special group. It'll be this special like oxygen bonded to a hydrogen. There we go. And so now I look at these molecules and I see different atoms, obviously. And so the electronegativity of carbon is probably a little bit higher than hydrogen. But the area of this molecule that really concerns me is right here. This is a really polar region. FON have the highest electronegativities on the whole periodic table. So when you bond FON next to little baby hydrogen, you get an extremely polar group where the electrons are really going to pull stronger to the oxygen.
Students, the buses are now in front of school. You may go out
Obviously,
to your buses.
that's going to happen with the carbon as well.
To go out to your buses.
Just not quite as
Have a great
extreme.
weekend.
Like carbon and oxygen do have different electronegativities, and oxygen's a little bit higher than carbon. Maybe just not quite as extreme as when oxygen bonds to hydrogen. But as the electrons pull toward oxygen, it becomes really negative, partial negative. And then this poor little hydrogen becomes partially positive. So now you can kind of see when a few of these ethanol molecules line up next to each other, they're going to be attracted to each other. And in fact, you'll even have those hydrogen bonds. One end, that OH region, can hydrogen bond to other molecules. Now the carbon-hydrogen region, the other region of the molecule, is really just kind of slightly polar and ends up with those dipole forces. But we can hydrogen bond because we're going to have some really polar regions, really strongly partial positive and partial negatively charged regions of the molecule. They'll be pretty attracted to each other. So if these molecules are more attracted to each other, they've got those stronger interparticle forces, especially the hydrogen bonds. These guys are going to be less volatile. It'll take more energy to separate these molecules because they're already a little bit more attracted to each other. Now obviously then that affects things like melting point and boiling point. Melting is the change from a solid to a liquid. And so yeah, if the particles have stronger intermolecular forces, it's going to take more energy to separate them. Same thing with boiling point, going from liquid to gas. If the intermolecular forces are stronger, the particles are more attracted to each other, I'm going to have to add more energy to separate the liquid particles so they can fly off into the gas phase. Now they also kind of mention here ionics and metallics. Ionics and metallics have really strong attractive forces. Ionics exist as those big crystals, right? Where I've got these oppositely charged ions in a very organized crystal pattern. Let's say I have something like NaCl. And we're not just talking about partial positive and partial negative charges. No, this is like a full-out +1, -1 transfer of electrons. This is stronger than a partial positive. And these oppositely charged ions then align in a very organized pattern. Positive, negative, positive, negative, positive, negative. And the attraction is extremely strong. And you also have something similar in metals where you've got the positive metal nuclei and the electrons, the sea of electrons, are kind of floating amongst the metal nuclei. But we're not talking partial charges. It's like a full-out +2 charge, or 2 electrons were donated to the sea of electrons. These ionics and metallics have the strongest attractive forces, just because their charges are really intense. Now the other thing that they kind of mention down here too is that all of this intermolecular force stuff is like a degree of strength. That it's not to say that all hydrogen bonds are stronger than dipole forces. And 99% of the time they are, but sometimes we can have London forces that even within multiple particles that have London forces, some can be stronger and some can be weaker. And so they kind of mention that down in here. That let's say I have a couple different diatomic particles. So here they're talking about chlorine, bromine, and iodine. Well, obviously, they're all just Cl2, Br2, I2. It's the same atom bonded to itself, so of course they're non-polar. And if they're non-polar, we would expect them to have those weak dispersion forces. Well, even within dispersion forces, some are stronger than others. It depends on the number of electrons. And so, for example, let's say I have, I'm going to switch gears and do like helium. So helium is a really small atom. Here's going to be helium. And it's got its positive nucleus. And helium only has 2 electrons. 2 electrons. So chances are it's pretty easy to keep those 2 electrons far apart from each other. There's only 2 of them. So 99.999% of the time, those 2 electrons are going to repel, and they'll go as far apart as possible within that 1s orbital. But now as you go to like bigger noble gas atoms, I could have argon. Well, here's maybe like an argon atom. Oh, I should do a different color. Let's say I got argon. Argon. So it's a little bit bigger. Argon. electron is number 18. So now let's say I have 18 electrons and they're distributed amongst more orbitals. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. There's my 18 electrons. Can you kind of see that I tried to put more electrons over in this region right here? And I have less electrons over here. The more electrons you have, the greater the chance that they're not dispersed equally amongst all their orbitals, that they're not perfectly distributed around the nucleus. And it's just a little bit harder the more electrons you have. It just takes a few electrons to be out of whack, and you could create these partial charges. I mean, now think about something then like xenon. I mean, xenon would be a huge atom with this positive nucleus, and xenon's going to have, good Lord, 54 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, somewhere close to 54. I lost count. But can you kind of see that now when I have 54 electrons, again, it's just going to be way harder to keep them all separated and perfectly distanced from each other. It's like if we only had 2 kids in the building, you could keep them socially distanced. But as I get more and more kids in the building or in a classroom, it's just harder to keep them all distanced, especially when they're free to move, like electrons do. That I'm trying to keep these moving electrons evenly spaced at all times. That the more electrons you have, the harder a task that is. And so then again, as I get more electrons that just randomly are in one area versus another, the area of the atom that has more electrons will for that moment in time be partially negative, and the region that's lacking the electrons partially positive. Well, it just means then that the xenon is more likely to have these dispersion forces, which then would make the dispersion forces a little bit stronger if it's more likely to happen or it happens more often. Or I can get a stronger partial positive and partial negative as I have more electrons. The same thing happens down here with the example of the diatomic chlorine. So the Cl2 molecule would have 34 electrons. But as you get to like the iodine molecule, it would have 106 electrons. That's a lot of electrons to keep perfectly organized and away from each other. And so even though like all 3 of these, the chlorine, the bromine, and the iodine, will all have these weak dispersion forces, they get stronger as you have more total electrons. And it affects things like phase. So the chlorine is normally a gas at room temperature, bromine is a liquid, and iodine is a solid at room temperature. The iodine particles are just going to have stronger dispersion forces, and they're going to be more strongly attracted to each other, which then makes it more likely that they're packed together in a solid. So here's an example of some hydrogen bonds. We have NH3, and they want the dominant intermolecular force between NH3 ammonia. But if you ever see hydrogen, you can think about hydrogen bonds, but it has to be hydrogen bonded to F, O, or N. Hydrogen bonding is fun, which we have. So yeah, it's going to have hydrogen bonds. But then it says, given that ammonia is a gas at room temperature, what can you infer about the relative strengths of the intermolecular forces between ammonia and between water? Well, I know that at room temperature, water is a liquid. So there must be something about the strength of the intermolecular forces between water molecules that's stronger than the intermolecular forces between the ammonia molecules. So if you think about the structure, let's say we have something like this. In a nutshell, Here's my NH3. And here's my water. And he's got his little lone pairs. And they're both polar molecules. They both have an unequal distribution of atoms around the center. So they're totally polar molecules. And they would both have hydrogen bonds. They have hydrogen bonded to F, O, and N. But now it becomes a matter of electronegativity. If I'm looking at the periodic table and I know fluorine is the winner, fluorine is the ultimate highest electronegativity, well, the next door is oxygen. And so oxygen has a slightly higher electronegativity than nitrogen. I mean, they're both really high, but oxygen's going to be a little bit higher. So even though they both have hydrogen bonds, they're going to be a little bit stronger in the water molecules. Because the electronegativity of oxygen is a little higher, it just means that oxygen is pulling on the electrons a little bit higher, a little bit stronger, so that we really get a strong partial negative and a strong partial positive on my hydrogens. The same thing is happening in the NH3, it's just not quite as intense. The electrons are still going to pull toward nitrogen. It's got a higher electronegativity than hydrogen. And the nitrogen becomes partially negative, and the hydrogens are partially positive. It's just not quite as extreme as when oxygen pulls from hydrogen. With oxygen's higher electronegativity, it's just a little bit more polar, and the hydrogen bonds are just a little bit stronger.